Hello and welcome back to PC Retro Programmer. In today's video we're going to be looking at how to draw lines in Tandy Mode 9, the 320 by 216 color mode. Now I already made a video on how to draw points in this mode, and a lot of the principles are going to be the same here. We're essentially going to take the best code that we have so far for drawing lines in CGA, the 4-color 320 by 200 mode, and convert it into code for the Tandy. So two of the big differences are that there are 4 banks of 8 kilobytes instead of 2 banks of 8 kilobytes on the Tandy, as you can see from the little chart on the left. And there are also 2 pixels per byte instead of 4. So this means that there are 4 bits per pixel within the byte. There's a high nibble and a low nibble, each representing a pixel with colors 0 through 15. So let's take a look at the code that I've written for this. I called this tandylin.asm. Lin stands for line here. And it's going to be very similar to the CGA code, but I've just modified it for the Tandy. Now the arguments to the function are the same as for CGA, except that the color is now 0 through 15 instead of 0 through 3. And I'm actually going to leave the register assignment alone as well. The only real difference here is the way that the mask and color bytes are laid out. So what we do on TGA is that we duplicate the color information in the low and the high nibble of the color byte, and then we select between the two using the mask byte. So it'll have all ones in either the upper or the lower nibble, and so ANDing with that will have the effect of selecting either the color information in the low half of the byte or the color information in the high half of the byte. And remember that in video memory you have 2 pixels per byte, and the left hand pixel is in the high 4 bits of the byte and the right hand pixel is in the low 4 bits of the byte. So simply by complementing that mask byte, doing a logical knot of each of the bits so that they flip, we can actually change from selecting the high half of the byte to the low half of the byte. So the leading code here is pretty much the same as for the pixel drawing code on TGA. So I've already covered that in a video, so I'm not going to go through it again. Essentially we just compute 2 times the offset, and then at the very end divide through by 2, and we also compute the color and mask bytes, which is all identical to what we did in the pixel drawing code. So let's start with the main loop for the vertical right moving lines, and I only really need to deal with one of the 4 cases in any detail here because the other 3 are going to be very similar. The code for actually drawing the pixel on the screen is pretty much what we had in the TGA pixel drawing video. First we make a copy of the mask and color bytes into the AX register just so that we don't mess up the originals. And then we AND the mask byte with the byte from video RAM. And this is initially set up so that it will zero out the bits that we're interested in, ready to put color information in. So then we need to get the color information, and we do that by complementing the mask and ANDing it with the color byte. And this will have the effect of now selecting the 4 bits of color information that we want, and then we just copy those into the video byte that we're updating at this step here. So now everything's updated and we can just write that byte back to video RAM. So that's how we draw our pixel. Now along the way here we actually complemented our mask byte, and because we actually used up the copy of the mask byte here, we actually ended up having to complement the original mask byte at this point. And we don't want to do that, so we need to undo it, and we accomplish that by complementing it again at the end here, just so everything goes back to square. Now we have our if statement here, that's the same as the CGA code, and then we come to the code for incrementing in the X direction. Now the way that we were handling this in the CGA case is we were rotating both our mask and color bytes right by 2 bits. And we were using the fact that if the low 2 bits of the mask byte were 0 before the rotation, then that is the condition where we need to increment our offset to move on to the next byte of video RAM. And so we used the fact that the carry flag would automatically be unset in that case, and so we would just complement it and use that to add with carry, in other words, to update our offset by adding 1 to it in that case. So we want something similar here, but it turns out that rotating our mask byte right by 4 bits, which is what we'd need to do here, would be very expensive. We'd have to have 4 shifts by a single bit, which would be a lot of machine code. And we can achieve the same thing for the mask byte simply by complementing it, and we can do that in a single assembly language instruction, which is much, much cheaper. The only problem is that this doesn't update the carry flag. And so what we need to do is find a way of figuring out what the correct condition is and then updating the carry flag just as if we'd done that rotation. Now, the correct condition is that the 4 bottom bits of the complemented mask have to be set. And so somehow we have to get from those 4 set bits to the carry flag being set. Now, I couldn't find a single assembly language instruction to do this, but I managed to do it in 2 assembly language instructions. And so this is what I came up with. First, copy that complemented mask byte into the AH register, and then copy that into the flag register. Now, the convenient thing about this is that the carry flag is the bottom bit of the flag register. And so if that bottom 4 bits of the complemented mask were set, the carry will now be set at this point. And that's exactly what we want for our add with carry to increment our offset. So that's how I handled that case. The next line of code is the same as for CGA, so then we come down to the code for incrementing the Y direction. Now here I thought I was going to have a real battle because there are 4 banks in TGA as opposed to 2 banks in CGA, and I really thought I'd end up with a whole pile of conditional jumps here to deal with all the cases. But it turns out that there are really only 2 things that we're doing here. We're either moving on to the next bank, or we're at the final bank and we need to move back to the first bank, in other words, go back 3 banks. So those are the only 2 things that we need to do, and these can actually be handled in precisely the same way that we handled the banks in CGA, where there were only 2 banks. So the first thing that we try to do is go back 3 banks. So obviously that means subtracting 3 times 8 kilobytes from the offset. And of course, when you go back 3 banks, you also need to increment the scan line. And so that means adding an additional 160 bytes in this case to the offset. And of course, since we're doing a subtraction here, not an addition, that becomes minus 160. And then the other thing that we need to do is we need to compensate for this STOSB that's up here. This will have incremented the offset, which we didn't want to do, and so we fixed that up by subtracting an additional 1 here. So this is precisely what we want to do if we did want to go back 3 banks. But if that was not the right thing to do, what will have happened is we'll have subtracted too much off DI and we'll end up with a borrow. And there we use our subtract with borrow trick to set all 1s in the AX register in that case. And then we can just AND that with a correction factor to do what we should have done all along. So first of all, we need to correct for the fact that we went back 3 banks, so we need to add that 3 times 8 kilobytes back on again, and then we need to move on to the next bank, which is what we wanted to do all along, and that means adding an additional 8 kilobytes, so in total we have to correct by 4 times 8 kilobytes. And of course, when you move on to the next bank, you don't actually increment the scan line. You keep the scan line the same and just increment the bank. So we'd need to undo this minus 160 here that we used to move on to the next scan line. and so that minus 160 also appears in the correction factor. Now the final thing is this plus 1, which was for correcting for the STOSB, and we actually do want to do that always, and so that plus 1 doesn't need to be corrected for, and so it's missing from the correction term. So now we have both cases dealt with, and so this is how the increment y gets handled, pretty much just like we did for CGA. So this is actually the end of the vertical right moving code, and so all that remains now for this line drawing code is to go through and make similar changes to all the other three cases, and of course this is pretty straightforward to do. The next case we deal with is the horizontal right case, and there's really only one new trick here that we need to talk about. So obviously the pixel drawing code is identical, and in this case the increment y ends up inside the if statement. It's exactly the same code that we used above, except that the correction for the S2SB can't be put in here because this is inside the if statement, it doesn't run all the time. So we handle that just as we did in the CGA case by doing a subtract with borrow down here instead, and that deals with the STOSB. So the only other change here is that for this subtract with borrow here, the condition is now basically the complement of the carry that we had in the vertical right case. So it turns out that we can actually avoid complementing the carry flag, and we get the complement for free with a little trick. So originally what we were doing here is we were first complementing the mask, then we were moving it into AH and then into the flag. But by switching the order of these here, I've actually got the complement happening after I've moved it into AH. And so this actually has the same effect as complementing the carry down here. But now just by switching the order of these two lines so that we're dealing with the uncomplemented mask, this actually gives us the same effect for free. So that's the nice little trick that we applied in the horizontal right case. And there's not very much to say in the other two cases. Basically, it's just exactly the same thing, mutatis mutandis, and we just adapt the original CGA code in exactly the way that you might expect. And in some cases we do the complement mask after and sometimes before, and obviously we just use our standard setting the direction flag trick to make STOSB decrement instead of increment, and otherwise everything is changed in exactly the same way as we did for the CGA code. And similarly for the horizontal left code, we again just make all the obvious changes. In this case, where the complement comes before, and it's back to being an add with carry. So that's the end of the line drawing code. So now we come to the code for actually drawing the lines on the screen. And that's the same basic driver code that we had in the CGA case, except that of course now I'm going into TGA mode 9 instead of CGA mode 4. And I also decided to pick colors that would really show up that were in a TGA mode rather than a CGA mode. So I picked colors 1 and 2, and then 12 and 14. So that's basically exactly the same otherwise. And so now let's save this and actually run it on original hardware after assembling and linking it, of course. So it's just tasm tandy lin, t-link, tandy lin, and now I'm actually going to run it on real hardware. This is the fruit of our labour. It first of all draws in colour 1, then colour 2, and 200 lines in colour 12 and 14. So it looks like we've had a successful port over to TGA, and I make it about 400 lines per second, maybe a little less, And this of course is running on a Tandy 1000SX with a 286 processor in it, but I don't think we've slowed anything down from the CGA case, which is great.